All right, now we move into the chapter on internal flow. I'm going to talk about a review of some of the material about Reynolds number, laminar flow, turbulent flow, and then talk about the friction factor, how to predict the pressure drop in flow or the head losses for pipe flow, as well as flow in fittings. So as a review, you can think about a pipe. You have the center line to the pipe, and you have the velocity profile in the pipe. If it's laminar, it's a quadratic velocity profile or parabolic velocity profile. What was the equation? Did we ever talk about U is equal to U max times 1 minus R over cap R squared? Okay. If that is the parabolic or quadratic velocity profile, how do we calculate the average? It's 1 over the area, the integral of U dA. And so you stick in that area, the velocity profile. We've done this before. 1 over pi r squared, integral from 0 to cap R of U max, 1 minus R over cap R squared, times 2 pi r dr. Cancel the pi's. Move these r's under here. Introduce the change of variable. So it's integral from 0 to 1, 1 minus x squared, 2x dx. And U average is equal to 1/2 U max for laminar flow. A clicker question. Water flows steadily through an 8 millimeter diameter pipe at a flow rate of 1.15 liters per minute. The flow is laminar. Calculate the velocity in the center of the pipe. So we'll go ahead and give you 30 seconds to answer this. So I'll take your responses now. Professor, would it be a different answer if the question read the average velocity in the pipe? Would it be a different answer if I asked the question the average velocity in the pipe instead of the velocity in the center of the pipe? All right, let's do this. What's the relationship between, this is AV is given, right? It's 1.15 times 10 to the minus 3 meters cubed per 60 seconds. That's the volumetric flow rate. And if I wanted V average, I would take the volumetric flow rate and divide by the area. So it's the area is a pi 0.008 meters squared divided by 4, and the volumetric flow rate 1.15 times 10 to the minus 3 meters cubed per 60 seconds, 0.38 meters per second. What is the speed or the velocity in the center of the pipe? Laminar flow. Laminar flow. Are you off by a factor of 2? If I say the V max is equal to 2 times V average, is that correct or incorrect? Isn't it C? You remembered the factor 2, didn't you? Yeah. All right. Here's one to help recuperate. What is the velocity halfway between the wall and the center of the pipe? Halfway between the wall and the center of the pipe. How long should we give you? 3 minutes? 4 minutes? There you are. Put it in. We're done, right? All right. So is the equation that V is a function of R or U is a function of R? Jump back and forth, unfortunately, between V and U for velocity, but it's down the X direction of the pipe. Is that equal to V max times 1 minus lowercase r over cap R quantity squared? Good or true or false? True. All right. If you're halfway between the wall and the center, is R over cap R equal to 1/2? Is that what it means to be halfway between the wall and the center? Lowercase r is halfway. So basically it's 0.76 times 1 minus 1/2 squared. Is that right? So what do you get for that answer? Is it 0.57? Congratulations. Just to review, volumetric flow rate, AV, we just used it, and the relationship you get rho AV is the mass flow rate, m dot. So this average speed is very important, but it's not the maximum speed, it's not the speed at the wall, or for laminar flow it's a parabolic profile. The velocity profile in a pipe of radius r is given by some non-parabolic profile. R, it's 1 minus r over cap r, all of that to the 1/6 power times u max. Okay, that's u as a function of r. Determine the average velocity in the pipe. Haven't we done that before? Very similar profile. Step through the process. It's just a challenge that you have u average is equal to 1 over the area, pi r squared. The integral of u max, times 1 minus r over cap r to the 1/6 times 2 pi r dr going from 0 to cap r. Take u max outside that integral, cancel the pi's, bring the r squared underneath, and underneath change a variable from lowercase r over cap r to x, change that to x, so it's equal to u max times the integral from 0 to 1 minus x to the 1/6 times 2x dx. Get some help or review how to do the integrals. Type it into Wolfram Alpha. So far it's been free, and you find that it's around 79.1%, and so the average is around 0.791 u max. This looks like turbulent flow. The profile is relatively flat in the middle. What does quadratic look like? Parabolic. It's much faster in the center. So what was the contrast if it was laminar? U average equal to what times U max? 1/2. True? True? Okay. So a review again on the laminar versus turbulent flow. Osborne Reynolds set up an experiment. He had a little die come in. He introduced that die. If the die stayed in the center as the fluid flowed down the pipe, then it was laminar flow. But sometimes as he increased the velocity, and as he increased the speed of the flow of the water, when he introduced the die would go and turbulent, laminar. It stayed in its layer, L-A-Y-E-R. I can spell L-A-Y-E-R. It stayed in its layer, its laminar flow. So we honor him today with the Reynolds number for flow in a pipe rho v d over mu, where d is the characteristic length, or in general, Reynolds number is just an unspecified length, some characteristic L, doesn't have to be diameter d. It's rho VL over mu. Well, how do we interpret this Reynolds number? Ratio of inertial forces which promote turbulent divided by viscous forces which promote laminar flow. Turbulent over laminar, inertial over viscous. Okay, what is, I know we can talk about force or force per unit area. What would be my inertial pressure or inertial force per unit area? So I want to interpret this as inertial pressure divided by viscous pressure. Okay, inertial pressure. In fluid mechanics, we've studied things. So what am I looking to put in the numerator? A pressure. How many different pressures? Some pressure associated with the speed of the flow. Another name for the pressure associated with the speed of the flow is dynamic pressure. What's the equation for dynamic pressure? 1/2 rho v squared. True or false? We're going to do a dimensionless ratio. That half doesn't matter. Okay? That half doesn't matter. I'm looking for the fluid properties like speed and density. That's what matters. It's not necessarily, because it's a ratio. It's a dimensionless ratio. Okay. What about viscous pressure? Okay, well, I don't like viscous pressure. I like viscous force per unit area, but it's not a normal force per unit area. It's a viscous stress. Viscous stress. What is equation? Tau for viscous stress. What is equation to help me calculate tau? Somebody's law of viscosity. Mu, some change in the speed with respect to some distance. So instead of a derivative, I just say v minus 0 over some distance. It's some change in speed. Well, it's probably 0 at the wall, no slip, and some speed in the middle. Just call it v. V average, v max. They're related by some constant, typically 79%, 50%, something like that. So it's v over L. So what you have is you have rho, cancel one of the v's. You bring that L up, so rho VL over mu. Guess what we have? Reynolds number. So the Reynolds number, don't forget it. It's probably on your FE exam. Multiple choice question. Reynolds number can be interpreted as a ratio of gravitational to viscous, buoyancy to inertial, inertial to viscous, and then you have your 5 choices, and in there will be something like inertial to viscous forces. True? True. The critical Reynolds number for when you see the difference between laminar and turbulent flow in a pipe is around 2300. So when the Reynolds number is less than that critical value, it is laminar. And when it's above, it's turbulent. For flow in a pipe, we're using the diameter as the length scale. Around 2300. Some books will have 2100. Some books will have 2000. It's around there. Okay? How about non-circular ducts or non-circular pipes? Well, compare it to the circular. And there's multiple of these. Here's a circular. This is, let's say, just not a square, but a rectangular duct. Okay? First of all, what is the area for the rectangular? Is it A times B? What is it for the circular pipe? Is the area pi d squared over 4? Good. What is the average velocity A would be the volumetric flow rate through it divided by the area. Is that how I get the average velocity? I would say, give me the volumetric flow rate. Let me divide by the area. That's the average velocity in it. True or false? So you could say, give me the volumetric flow rate and divide by A times B. Good. How about for the, why did I write A there? Oh man, come on now. Average velocity for flow in the pipe would be the AV divided by A. True? Good. What is a perimeter? Perimeter. It's where you have that no slip boundary condition. For a given cross section, it's the length. Perimeter is a length. So it'd be A plus B plus A plus B. So the perimeter is equal to 2A plus 2B, or simply just 2 times A plus B. How about the perimeter for a circular? It's an inner diameter, that's right. So perimeter is pi, 2 pi r, or pi d. Is it pi d? Good, it's 2. Now we introduce to the hydraulic diameter. The hydraulic diameter, d sub h, is defined as for the cross-sectional area divided by that perimeter, the no-slip or the wetted perimeter, the different ways of describing it. So what is the hydraulic diameter calculated for a circular pipe? Well, 4 times A pi d squared over 4 times the perimeter pi d. So we cancel the 4's, cancel the pi, cancel one of the d's, and you find that, hey, the equation for the hydraulic diameter, when you apply it to a pipe, gives me back the physical diameter. Makes sense. How about if we apply it to this section, d sub h? Well, you get a appropriate measure of some diameter, some hydraulic diameter. So it would be 4 times A times B divided by 2 times A plus B, or it's just 2 times A times B divided by A plus B, whatever it is. D sub h, true? You would just compute it. You would just compute the hydraulic diameter for that condition. Now there's triangular, there's elliptical, there's all kinds of shapes for different cross sections. The book shows a few of them, and it's in table 8.1. We'll get to that in a minute. But this concept of hydraulic diameter, how would you use it? Well, you would use it to estimate the Reynolds number. If I wanted to get the Reynolds number for flow in this pipe right here, RE, how do I calculate it? I need rho V hydraulic diameter over mu. How do I get this V? It's right here. Right? The volumetric flow rate divided by the area gives me that average speed used in the Reynolds number. How do I get the hydraulic diameter? Right there. Do you have a comment or question?
Yes, sir. I'm wondering about that hydraulic diameter on that circular pipe. Where did that fourth denominator come from?
Well, it's pi d. The area is pi d squared over 4, and I had a 4 over perimeter.
I see it now.
Got it? Okay. Here's a problem. We have airflow through a 5 centimeter by 8 centimeter cross-sectional rectangular duct. The average velocity is given to be 4 meters per second. Calculate the Reynolds number and answer, is the flow laminar or turbulent? And I'm going to let you do a clicker question. A, if you think it's laminar, and B, if you think it's turbulent. Okay, so answer this question. First, make a calculation of the Reynolds number. And once you calculate the Reynolds number, select if it's laminar or turbulent. All right, we're there. Yeah, hopefully everybody was able to get it in. So what do? You need to calculate the Reynolds number, which is rho v d hydraulic divided by mu. And so we're going to need the hydraulic diameter. It's 4AC over perimeter. 4 times the 5 centimeters times 8 centimeters divided by the perimeter, which is 2 times 5 plus 8 centimeters. One of the centimeters cancels, but don't forget that that is in centimeters. And so you calculate that that is 6.154 centimeters for the hydraulic diameter, which goes here. The velocity is 4. The density is this number. The viscosity is that number. 16,700. Turbulent. Turbulent flow. So it's turbulent. See how we did that? When you have flow that starts into a pipe, maybe from a large tank, the flow may not be parabolic. If it's going to be laminar flow eventually, it may take some length of time before it becomes what they call fully developed. So as it goes down the tube, maybe when it's down here, you do have a fully developed laminar velocity profile, or if it's going to be turbulent, it'll have some more flattened but a more turbulent profile, but it'll be fully developed, meaning the profile doesn't change as you go further down the tube. But when it first comes in, maybe it's very flat in the core but sharp at the edges, and then it takes a while for the effects of the viscosity to be felt throughout. And so what you grow is a boundary layer, but you're growing it all the way in until the boundary layers meet, and then you're fully developed. This length is an entrance length. That's how much length is required to become fully developed. And then once it is fully developed, then after that, the profile is not going to change. So this layer, this velocity boundary layer concept dictates how long it takes for it to be fully developed. We talk about hydrodynamically fully developed. This course is a prerequisite to another course called heat transfer. You could have a cold fluid with hot walls, and you would have to be thermally becoming fully developed, where you get a temperature profile in the pipe. So that's why here it's hydrodynamically is the velocity profile fully developed. Later, next class, is it thermally fully developed? And different parameters, Prandtl number will tell you, does it develop quicker thermally or slower thermally? If the Prandtl number is around 1, they develop at the same rate. Well, how do I predict this entrance region? The entrance length is around 10 diameters. It doesn't matter if you're how much above the critical Reynolds number. There's other equations. I think the book has one as well, but roughly 10 diameters is a good number to remember. After 10 diameters, you're fully developed. For laminar, the entrance is 1/20th of the Reynolds number of diameters. So if the Reynolds number is going to be 200, you would say, hey, that's laminar flow, isn't it? Reynolds number is low, well below 2300. It's going to be laminar flow. Then you would find that this is around 200 divided by 20, 10 diameters. But if the Reynolds number goes up, let's say the Reynolds number is 2000, it's starting to maybe trip and become turbulent. If it keeps going up, it will become turbulent. So how long does it take? So you have 2000 divided by 20, around 100 diameters. True? So It can take longer if it's laminar flow, close, getting up there over 200, 500, 1,000, up 2,000 Reynolds number. All right. Where is this practically important? A lot of times they'll have piping systems, and somebody will say, I need to stick a flow meter into the piping system. But the flow meter is anticipating fully developed either turbulent or laminar flow. Almost always it's fully developed turbulent flow is what it wants, right? And so what they'll do is they'll say, if you're coming around a bend, or if you've recently added fluid into the pipe, you have a union and two pipes coming together and a third pipe going out, you need to put that flow meter about 10 diameters downstream of the last disruption that would make it kind of restart hydrodynamically so that it becomes fully developed. And if you ever go out and practice and you're working as an engineer, you have to walk through facilities and look at flow meters or put the flow meters or check the flow meters. It's not uncommon to find that whoever installed it found that there was some obstruction or something that prevented them, and they snuck it in at 2 diameters or 3 diameters afterward. What's it going to do? It's going to give you a bias in that flow meter. It'll be a continual bias in the reading of that flow meter. So that's one thing to have fully developed flow. We did this before, but I want to do it in detail, and it's to develop the differential equation for laminar flow in a pipe and then solve for the velocity profile. So bear with me here. We have pipe flow. And what do I have around the center line is I have an Rx coordinate system, and I'm interested in doing a force balance on a little differential element that looks like this. That differential element goes from x to x plus delta x. It also goes from r to r plus delta r. Okay. Acting on that little element, we're going to have the pressure at the location x pushing in the positive x direction. We'll have the pressure at location x plus delta x, but what direction does that push? In the negative x direction. And what is the area that the two pressures act on? It acts on 2 pi r dr. That's the area it acts on. It's that ring area. Then we have viscous forces. Now it's a little harder to see. Maybe I flatten it out and just say, right here is my little element. Here's the center line. The flow on the inside is going faster or slower than the fluid in that little ring annulus. The fluid is flowing faster. Hence, the fluid is going to exert a force, a shear stress, in the positive x direction. But the fluid on the outside is slower. It's going to have a shear stress that's going to be in the negative x direction. So what do we have is we have the shear stress tau at r in the positive x direction. Multiply that by the area on the inside, which is 2 pi r dx, and then negative shear stress at r plus delta r times 2 pi r plus delta r dx. I have two pressures, two shear stresses, 4 areas that I'm dealing with. The sum of those forces is equal to 0 in steady state flow. Yes, sir.
So where is the second pressure coming from if you have one flow going?
It's right here pushing back.
Yeah, where is that coming from?
That's because the pressure is dropping as I go down the length of the pipe. The pressure in the pipe, in a real pipe that has viscosity, we do have viscosity with the shear stress and the viscous shearing, will have a pressure drop as I go down the pipe. And that's what gives us the velocity profile, no slip at the boundary, and then at the center you have that maximum speed. Okay, so at this point what we want to do is take this equation. Let me ask and pause for a minute. Did I make a mistake, or does it look okay to you? Do you see where each of those terms come from? So the game then is to divide by dr dx. dr dx. The dr's cancel. The dx cancel. In the limit for smaller dx and smaller dr, what we get is also let me cancel the 2 pi's, right? 2 pi, 2 pi, 2 pi. They're all canceled. And so now what do we get? We get negative dp dx in the limit. And then what do we get here? Negative derivative with respect to r. The viscous shear stress tau times r. Good or not good? What is it? Good? Do you agree? All right, that is equal to 0. If we use Newton's law of what? Viscosity? What does Newton's law of viscosity say? Shear stress is equal to mu du dr in this case. Okay? But let's play with this a little bit. I'm looking at this. This is the direction of increasing r, true? My velocity profile is going to be du dr. Is that positive or negative? As I increase r, does u go down or up? Maybe what I do is to make it more familiar with you, you flip it like this, and here's the center line, and here is r. R starts at 0 and it's going to go out to cap r. True? Kind of take it in your mind and flip it. Then the velocity profile I'll plot going up for u this way, u, and it'll be like this. All right, so the slope of this line is negative. That's true, it's negative. So if I have mu du dr, okay, and it's negative out there, if I evaluate it on this face right here, does that give me a positive shear stress in the positive x direction like I wanted? I need to put a negative sign right there. So it's minus mu du dr. All right? Okay. So let's go ahead. I'm going to scroll down. And we have minus dp dx. And we have a minus. Let's just leave it in there. Dr minus mu du dr times r equal to 0. I got a lot of minus signs, true? Should we get rid of some of them? So we'll have mu derivative with respect to r of r du dr equal to dp dx. Did I make a minus sign error? Hopefully not. This is an ODE, which I can use to solve for u as a function of r, and then get that quadratic profile. We have never done this, but we're doing it now. We're proving that quadratic profile for laminar flow. But I need, for this second order ODE, I need a boundary condition number 1 and a boundary condition number 2. I need two boundary conditions. So at the derivative of u at r equal to 0, what is that? Slope of the velocity profile. Because it's symmetric at the center line, it's 0. The slope is 0. And then what about u at lowercase r equal to cap r? What's that? So symmetry gives us one boundary condition. No slip gives us the other boundary condition. I put on my mathematical hat. I forget about engineering. And I just separate and integrate and try to solve this problem. Let me try and stuff it over here. So we'll do the mathematics right in here. So if you separate, what do you get? You get mu. Well, actually do this. Put this mu over here. Yeah, just do it over here. Derivative with respect to r of r du dr equal to dp dx times 1 over mu. This is a constant. We have fully developed flow in a pipe. The pressure is just going to drop as I go down the pipe. The pressure is going to drop the same amount per every foot or meter of length of that pipe. It's a constant pressure gradient as I just go down a straight pipe. It's fully developed laminar flow in the pipe. So that's all a constant. Treat that as a constant. So I separate. I put a dr over here, get rid of it there. I integrate. Let's just use the constant of integration. I think most people are familiar with it, or you can play with the limits on the integration to avoid that. But you get r du dr equal to dp dx 1 over mu r plus c1. What limit or boundary condition do we want to apply first? So boundary condition number 1 comes into play. If the boundary condition on number 1, it's like 0 times 0 is equal to 0 plus c1. What's 0? I mean c1. 0. So we're done with using that boundary condition. And we got rid of c1. So now let's rewrite that. Du dr is equal to dp dx 1 over mu. The r's cancel, right? Right. And so now if I integrate that, u, hold it. I left out an R. That R right there, right there, right there, needed to be right there. Sorry, I got to back up and throw them in here. There's my R. There's my R. There's my, so right here, this R became 1/2 R squared. Still the C1 is 0, but I pick up the 1/2 r dr, so one of these r's canceled like that. Okay, now we separate and integrate, so you have du equal to dp dx 1 over 2 mu, the integral of r dr, like that. So pick up u is equal to dp dx 1 over 2 mu, and we'll pick up 1/2 r squared plus c2. All right. What about that second boundary condition? You apply the second boundary condition, and what do you find? 0 is equal to dp dx 1 over 4 mu cap r squared plus c2. What's c2? The negative of that. And so now we can simplify, if I can do this correctly. U is equal to 1 over 4 mu r squared dp dx Then we'll have a minus sign right there. And we'll have 1 minus lowercase r over cap R squared. I tried to simplify the number of steps in algebra, but does that look reasonable? Yes or no? Look okay? Now, this pressure, dP dx, it's a constant, but also take a look. Remember when we were talking about that at first? What does the pressure do in the direction of increasing x? Does it rise or fall? It falls. There's a negative. So dP dx is less than 0. It's negative. So it's helpful to put a negative with dP dx. That means it's a positive. Everything here is positive. This is all positive. Okay. Well, guess what all of that is equal to? Isn't it U max? 1 minus r over cap R squared. There you go. So you'd have that the maximum speed, U max, is equal to r squared negative r squared dP dx divided by 4 mu. Somebody says, I prefer to work in diameters. Okay. Well, a diameter and 2 radius are the same. So I'll square that. So this is 1 over 16 negative 1 over 16 mu dP dx times d squared. Did I do that correct? Okay, so U max is equal to that. Somebody says, I'd like to get the relationship U average instead of U max. Well, U average is 1/2 of U max. So U average is negative 1 over 32 mu dP dx times d squared. So far, I only know I made one big error, right? I think the rest of this is okay. I fixed it, went back and found it, fixed it. All right. So now what we can do is we can talk about the pressure loss. Somebody says, how do I calculate the pressure loss in my pipe? Well, if I knew the rate of pressure drop and I multiplied it by the length of the pipe, wouldn't that give me the pressure drop? If I put, because a lot of times you put a negative on that term because it makes it a positive quantity. That would be the pressure drop. Does that make sense? All right. So let's do this. What is the definition of the friction factor? It's like the Euler number last time, but the friction factor is introduced to be the negative dP dx times d divided by 1/2 rho v average, or the average speed squared, 1/2 rho v squared. What is 1/2 rho v squared? That dynamic pressure. Some people will put this, they'll put pressure loss times d over L divided by 1/2 rho v squared. It's the same. This is negative dP dx is pressure loss divided by the length. True? All right. Well, if that's the definition of the friction factor, so we can say, well, it's the negative dP dx times d divided by 1/2 rho v squared. Let's do this. Can I substitute in for dP dx? How about we substitute in for dP dx right here? The negative dP dx. Okay, let me rewrite this. Negative dP dx is equal to 32 mu U average or V. Let's just change this now to V for speed. All right, divided by d squared. Does that make sense? So we're going to substitute right there. So this is now equal to 32 viscosity, speed, diameter divided by 1/2 rho v squared. The 1/2 goes up, 64. Cancel one of the v's, and you get I left out the d squared, didn't I? I left out this d squared right there. I cancel one of the d's. Is that good? Are you with me? All right. So we get rho vd over mu. That's unitless, and so the friction factor is 64 divided by the Reynolds number based on the diameter. For laminar flow in a pipe, that you get that the friction factor is equal to constant 64 divided by the Reynolds number.
And you can only use 64 Reynolds number for laminar flow.
That's only for laminar flow.
You solve for the friction factor using the mu velocity density number d.
How do we use this? Now, maybe this helps. How do I use this result? Well, I unravel the definition of the friction factor. If somebody said, calculate the pressure loss in the pipe, I'd say, give me couple things. Give me the friction factor, tell me the length of the pipe, tell me the diameter of the pipe, and tell me enough so I can calculate the dynamic pressure of the flow in the pipe. So when I want to calculate the pressure loss in the pipe, I unravel the definition of the friction factor just like this. So now if it's laminar flow, I know what this is. It's 64 divided by the Reynolds number. If it's turbulent flow, another strategy to get F, but we will get a numeric value for F. Then I have the length of the pipe. You see that if it's a longer pipe, greater pressure drop. If it's a smaller diameter pipe, for the same friction factor, a greater pressure drop. And then if it's really going fast, I have a higher dynamic pressure, greater pressure drop. So that's how we often use it to predict pressure losses. I already did this. Water at 5 degrees C at that temperature, here's the density and the viscosity. Flows steadily through a 3 millimeter diameter, 9 meter long horizontal pipe with an average velocity of 90 centimeters per second. Determine the head loss. How am I going to find the head loss? And then get the pressure drop, and then the minimum power for a pump to overcome that loss, to continually the flow through that system to overcome the loss, the power that the pump would need to supply. So let me just talk out loud here. I'm looking for H of L for the first answer. I'm looking for piece of L for the second answer. And I'm looking for W dot for the third answer. This is a head. Yeah, sorry, it's a head loss. Typo there. So what is my equation if I unravel the friction factor? The equation is, this is the friction factor, length over diameter, and then I have not a velocity pressure, but a velocity head, which is V, let me get rid of this underlining here, V squared divided by 2G. If I'm interested in pressure loss, same friction factor, same length over diameter, but I have my velocity pressure or dynamic pressure of 1/2 rho v squared. The only thing that really changes in that last parenthesis, is it 1/2 rho v squared or is it v squared over 2g? Okay, so what I do for this problem is I evaluate the Reynolds number. So it's rho vd over mu. The density is 1,000. The velocity is 0.9 meters per second, 90 centimeters per second. The diameter is 0.003 meters. And the viscosity is 1.5, 2 times 10 to the minus 3. So if you can run that for me, tell me what the Reynolds number is, please. All right, is that laminar flow or turbulent flow? Laminar flow. We'll assume it's fully developed. Forget about the entrance region. It's fully developed laminar flow. What's the friction factor? What's that number? 0.036. So now we can calculate this head loss is 0.036 times the length. The length is 9 meters divided by the diameter, 0.003 meters, or 3 millimeter diameter, times this v squared. It's 0.9 meters per second squared divided by 2 times 9.81 meters per second squared. 4.46 is the head loss. What are the units on that? Meters. True. And how about the pressure loss? Well, you can do this. If you already know the head loss, what's the relationship between the head loss and the pressure loss? If I multiply by rho g, or the weight density, gamma, of the fluid, I'll be able to convert it. And the weight density is 9.81 kilonewton per so 43.8 kilonewton per meter squared, or kilopascal. How many people agree? Do I got other people running with it? Thank you. The last part, what's the minimum power, pumping power, required to overcome this loss? Well, you either have to get the volumetric flow rate, or the mass flow rate, or the weight flow rate, but I don't have a symbol for the weight flow rate. But probably the easiest one, since we already have the pressure loss, is the volumetric flow rate. So if you calculate the volumetric flow rate, it's pi d squared, 0.003 squared divided by 4, times the speed, 0.90 meters per second. So what do we get for a volumetric flow rate? Anybody get that? Well, it's a
6.36 times 10 to the negative 6 meters cubed per second.
Yeah, okay, well.
Yeah, meters cubed.
Does anybody confirm that? Couple confirm? Now, if I wanted to calculate the power, is it at the volumetric flow rate times the pressure drop? The pressure loss? 0.28 watts. So you took into account that 1,000 on the kilo. So there you go. W dot is about a third, a little less than a third of a watt. You don't have a whole lot of flow. I have a couple people confirm that for me. You did? Good. Is ready to go on? Let's go ahead and go on then. What happens if I have laminar flow in non-circular pipes or tubes or ducts? Well, you're going to find that the friction factor is some constant divided by the Reynolds number. That's the general pattern. And if you take a look at table 8-1 in the textbook, it gives it to you for different ratios. Let's say if I go back to that rectangular duct and they say, well, if A divided by B is 1, then that constant or the friction factor is 56.92 divided by the Reynolds number. That constant's not 64, it's less. What happens if it's not a rectangular duct, but its ratio is 2? It's not a square duct, but it's a different ratio, like 2. Then it's 62.20 divided by the Reynolds number, etc. So what you do is the pattern of having the friction factor proportional to, equal to a constant divided by the Reynolds number. That's the general pattern for triangular, elliptical, rectangular ducts, as well as circular. Okay. All right. This is a long question. Hopefully we have enough time. Water flows through a square channel with smooth surfaces. So there's my channel. It's square. The flow is laminar. It's laminar flow. And the average velocity of the fluid is now doubled. So think about the initial case. Case A is my initial. And then we have the final case, case B. And they say that the velocity in case A and then the velocity in case B. Well, the velocity in case B is I doubled the speed, didn't it? The average velocity of the fluid is doubled. Okay. Assume that flow remains laminar. So it was laminar here. It's still laminar here, even though I doubled the speed. So the first question is how does the Reynolds number change? Does the Reynolds number remain unchanged? Does it increase by 50%? What would that mean? That the Reynolds number for case B is 1.5 times the Reynolds number for case A, right? If it increased by 50%, then it's 1.5 times the original value. Or does it increase by 100%, or 141%, or 200%? Let's answer this question first. How does that Reynolds number change? Do you need more than 30 seconds? There you go. 1 minute. Everybody in? Last chance. All right, everybody's in. So you have to remember that Reynolds number for case A, just like the Reynolds number for case B, is some rho, some V, some diameter, hydraulic diameter, divided by mu. Did the density change? Did the viscosity change? Did the hydraulic diameter change? No, what really changed was the velocity at B is now greater than the velocity at A. So if I replace V sub B as 2 then what do I get? I get that it's 2 times the Reynolds number at A. True? So I look over here, and I know it's tricky, but isn't that an increase by 100%? Is that true or not true? Very good. Let's now attack this next part. How does the friction factor change? How does the friction factor for case A, friction factor for case B? I'll go ahead and start it, and you want some extra time? Minute 45. Minute 45 for the friction factor. How does the friction factor change? So how do you describe that? It's half of what it is, so it decreased by half, 50%. True? Why is one person, your battery's low? I don't know. All right, I think this next one is okay. How does the head loss change? How does the head loss change? How much time do we want on this one? 2 minutes.
You can scratch my hands.
All right. So the friction factor for A is calculated, and then we calculate, not the friction factor. We'll talk about the head loss for A, and then the head loss for B. Well, what's the equation for the head loss? Isn't it that it's some friction factor times some length over diameter times some 1/2 VB squared divided by 2G, or however you want to write that. It's 2G over. True? And then we said, oh, I'm so glad that we already worked out that the friction factor for B is 1/2 the friction factor for A. The length and diameter haven't changed. And the velocity of B, I'm so glad we worked that out. That's 4 velocity of A squared divided by 2G. True? And so I find that this F of A times L of D times this term gives me back the head loss for case A, and then I have this 4 divided by 2. 4 divided by 2 is 2. So the head loss doubled, which means that there was an increase by Did I do that right? All right. Turbulent flow. Majority of flow in pipes and tubes is turbulent. I'm glad that we have all this analytic analysis of results for laminar flow, but most of our cases it's turbulent. So it's disorderly flow, it's rapidly fluctuating, it's swirling fluid, it's well mixed. The velocity profile is blunter in the core and sharper at the edges. Okay? That's the velocity profile. When we do a dimensional analysis of the problem, somebody says, well, my wall isn't smooth, and so I want to characterize the roughness of the wall, epsilon. It's some sort of so many millimeter roughness on the wall of the inside of the pipe. And then I still have that average diameter, inner diameter of the pipe. And what we find is the friction factor, dimensionless pressure loss, is proportional to the Reynolds number, how fast the flow is going, if it's going to be laminar or turbulent. But now we're all turbulent. It's really out there. It's how fast is it going. And how rough it is compared to the diameter. It's epsilon over d, the relative roughness. This is dimensionless, this is dimensionless, this is dimensionless. But the dimensional analysis doesn't, it just tells you the relationship, it doesn't give it to you. So what we do is we apply it to a bunch of experiments, and then you do some curve fitting, going all the way back to before you were born, 1939. Colebrook put out an equation. It looks like this. There's the friction factor, there's the relative roughness, there's the Reynolds number, and there's the friction factor, and it's on both sides of the equal sign. So if I was given the relative roughness and given the Reynolds number, if I wanted to use the 1939 version Colebrook equation, I would have to iterate. It's not really easy, but you could do it. Well, in 1983, Holland came out with an equation. He said, look it, give me the relative roughness, give me the Reynolds number, stick it into an equation, and you can work through and get, without iterating, the friction factor. That's great. There's been many, many, many others that have worked on this problem, curve fitting the data. But one accomplishment, one person named Moody put out a diagram, and he wasn't even the first to plot it this way, but he plotted it very comprehensively with a lot of data. And I forget the years he did it. I think it was in the 50s. Maybe it was the 40s. And so this is probably the most famous plot in all of fluid mechanics. So what's on the x-axis of this diagram, this Moody diagram? Reynolds number. It starts at a value of roughly 1,000. What do we know about flow at 1,000 for pipe flow? Laminar. It then goes to 10,000. Then 100. Then 1,000,000. 10 million. That's quite a range of Reynolds number, isn't it? And most of the X scale would indicate it's turbulent flow. But way over here on the left, it's laminar flow. What's on the Y scale? Friction factor. Is that my F? Yep, that's your F. Now, some people will write the friction factor somewhere on the Moody diagram to remind you what it's defined as. I grab this plot. I like to grab different plots out of different sources and say, do you agree? No, look it. I didn't even slow down the question. Do you agree with this definition of the Reynolds number? I'm glad he put it on the x-axis. Does it look good to you? Thumbs up if you like it. Now the friction factor, y-axis. Always takes us a little time to work through that. Do you like this definition of the friction factor? I can't hardly read it, so let's even rewrite it maybe. If I rewrite that friction factor, he's saying that it's F is equal to 2 diameter divided by rho v squared L. That's my L length, diameter length, delta P. Does it look good? If I put the 1/2 down here, 1/2 rho v squared, then I put maybe the D over L up there. Yeah, I got the pressure, delta P, the pressure drop, times D over L divided by 1/2 rho v squared. It looks good. Does it make sense? But go slow. Sometimes it's not so good. Yes, sir.
Are all these D's like hydraulic diameter?
If it's not, first of all, if it's pipe flow, all of this data is going to be for pipe flow.
Okay, yes.
Then yes. But you will see people use the Moody diagram using the hydraulic diameter for non-circular, and it's fine. It's fine. You just need to know that that's an additional engineering assumption that that's going to be close. Okay, so this is a friction factor. Now, this varied a number of orders of magnitude on the Reynolds number. What about the friction factor? It starts around 0.01, and it ends around 0.1, a factor of 10, true? This Reynolds number was a log scale. Can you tell me if it's either linear or log for the friction factor? Oh, you want a clicker question? Okay, A, it's linear, and B, it's log. And so A is linear scale for the friction factor, the y-axis, or B, it's a log scale for the friction factor y-axis. People are now calling for clicker questions. Hope you got it in time. I only gave you 30 seconds, right? So let's do this. What is the distance length here? What is the change in the value from 0.01 to 0.02? Isn't that a change of 0.01? That's a 0.01 change. What is the difference between 0.09 and 0.1? Isn't that a 0.01 change? So that's a 0.01 change, and that's a 0.01 change. Log scale. Log scale. Very good. Oh, you guessed right, huh? Now, notice over here, they plot in the laminar region one curve, and it's just a straight line on a log-log plot. The friction factor is equal to 64 over Reynolds number for flow in a pipe. This is pipe. Okay, and that says right here, laminar flow. You don't even need this chart. You give me the Reynolds number, put it into this equation, F is equal to 64 over Reynolds number, you have the friction factor. Okay. They also say, here are some reminders of some materials with their relative wall roughnesses. Concrete, very rough, but you come down here and you have some cast iron and some other things. Plastics and glass and drawn tubing have either the highest or the lowest value of epsilon. What do you think? Lowest. It's very smooth. Very smooth. It's not very rough. Epsilon's very smooth. Okay. Then what they do is they have a series of curves that are out in the turbulent region. The curves depend on different values over here. What are they plotting for? Like this is the curve per 0.002. Here's the curve 0.002. But what does that 0.002 mean? It's the relative roughness. Epsilon over D. True? So this is a rough pipe with rough walls compared to the diameter. This is a smooth pipe down here. And guess what this bottom curve is? Oh, look at there. Clicker question, Professor. A for smooth and B for coarse, rough pipe. No, it's smooth pipe, right? So that's it. So increasing roughness. And often it's put over here for those scales, for the relative roughness. Yeah, usually what happens is they say, this is my flow rate, this is my diameter, this is my type of pipe, so I get the wall roughness, and then I go in there and I calculate epsilon over D, maybe it's, 10 to the minus 5 right here, let's use that as an example. And my Reynolds number is 10 to the 6, so I find 10 to the minus 5, 10 to the 6, and I read off that value of friction factor so I can predict the pressure loss. That's how you use a chart. Okay? All right. So that's all of these curves. It can be overwhelming. But there's one other curve that's a little challenging to understand. It's this dashed curve. It's this dashed line. And what happens to each of these curves, let's say this one for the relative roughness of 0.002, to the right of the dashed curve versus to the left of the dashed curve. Tell me a little bit about that curve for relative roughness 0.002. Horizontal flat versus curved. It's not. So if I was out here at this relative roughness and I had a Reynolds number of 10 to the 6th right there is the friction factor. See that? Okay, somebody says, no, it's not 10 to the 6, it's 10 to the 7. That's a tremendous increase in the Reynolds number. How did the friction factor change? It's the same friction factor. So at some point, it's not dependent on the Reynolds number anymore. At very high Reynolds number flow, it's Reynolds number independent. And the friction factor is a constant for pipe flow. That's everywhere to the right of that dashed line. They have different names for that. They'll call this whole region out here complete turbulence or fully rough or whatever. There's some different name. But what it is it's saying, in general, I have the friction factor a function of Reynolds number and relative roughness. True? In this region, it truly is a function of both the Reynolds number and the relative roughness. But to the right of that dashed line, in the fully turbulent or fully rough region, it's only a function of the relative roughness. It's not a function of the Reynolds number. This is a very important chart. I don't know if I've asked a fluid mechanics class like this before, but when I teach a class that requires fluids and maybe heat transfer as a prerequisite, maybe a technical elective, I've told students, memorize it. Every detail. You can come in with a blank sheet of paper and reproduce it. It's an easy exam question. I usually make it worth 10% or something like that. Well, I tell them it's going to be on there, and then they memorize it. But I would hope that you would get the pattern, because this is not in the top 10 of important charts in fluid mechanics. It's like the number one. This is it. It's the Moody diagram. If you graduate, I passed the class in fluid mechanics. Somebody asks you anything about the Moody diagram, the Moody chart, something like that, and you say, I've never heard of it. We got a problem. It's like, you passed dynamics. Tell me a little bit about acceleration. Who? What? Never heard of acceleration. No, you can't do that. Pass statics, free body, what? There's no free bodies in the whole class. Free body, I never heard of a free body diagram in my life. No, you need to go back to statics, true? Moody diagram, you pass fluid mechanics, you must know it. All right. So how do we use it? Just like I described. Here's another diagram. What do they show here, which I like? 2,000 to 4,000. What's in this region? Kind of no man's land. They have different names for it, but it's really could be laminar, could be turbulent. Actually, it's somewhere in between. And a lot of times they just make those curves kind of join together like that. But it depends on some other initial conditions or some vibration in the system or other things. Often in real machinery, stuff is really vibrating. And so it helps it promotes turbulence. That's about it. Here, dividing line between zone of complete turbulence and transition zone. This is your transition zone, and then complete turbulence. Do I like this terminology of complete turbulence? No, I'd rather say something about Reynolds number independent zone, because it's not dependent on the Reynolds number anymore. Well, I am done for today. I thank you very much for your attention. We'll pick up there next time.